Recently in one of my weekly live streams, which I'm doing every Monday night at 5 o'clock Pacific time, I talked about partial fraction integration. And, one of the steps in that is decomposing partial fraction problems into smaller, simpler fractions to integrate, also known as partial fraction decomposition. And I thought you might find the portion of that live stream helpful where I talked about that. So I wanted to show you in this video how you can apply partial fraction decomposition in order to basically split a complex fraction into the sum of simpler fractions, which, if you're applying that to integration, should make the problem a lot easier to integrate. So by the end of this video, you should be a lot more comfortable with the partial fraction decomposition process. If that sounds good to you, be sure to stick around to the end of the video. But without further ado, let's go ahead and jump on into the example. Write out the form of the partial fraction expansion of the function x squared over x squared plus x plus 2. So in this first example here, we're not going to be going all the way through the problem, right? We're not going to be integrating this function, which you would frequently see with partial fractions integration problems. Instead, we're just going to take a moment to kind of think about what the partial fraction expansion of this function would be if we were to integrate this function and do partial fractions integration. Basically what this process is it's the partial fraction decomposition, or basically expanding it out into these simpler fractions that are going to be easier to integrate. Because what that does is, well, like I said, it just gives us two or more simpler functions to integrate. So it really just makes the integral a lot easier for us. So looking at this right off the bat, really with any sort of partial fraction type problem or type of problem where you're trying to integrate a fraction like this, you want to look at the degree of the polynomial on the top and the bottom of your fraction. So the degree of a polynomial is just saying what is the highest power that you're raising your variable to. So in this case, what is the highest power that we're raising x to? Well, on the top, there's only one term. It's x squared. So the highest power of x on the numerator, or the top of our fraction, is 2. Same thing with the bottom. We have an x squared term, we have an x term, and we have a constant term. The highest power of x is 2. So both the top and the bottom of this fraction, the numerator and the denominator, they both are degree 2. So since we have the top and the bottom of our fraction with the same degree, that tells us that we want to start this out by applying long division of polynomials. So if you have the top of your fraction having a higher degree or the same degree, so in other words, if the degree of the numerator is greater than or equal to the degree of the denominator, then we typically would want to start out with long division of polynomials. If the degree of the denominator is greater than the degree of the numerator, we don't need to do that. But since they're equal in this case, we do want to start out with that long division. So to do long division of polynomials, you're just basically going to take what your numerator is, so in this case x squared, and that's going to be within the division, because basically, when you're doing a fraction, the top divided by the bottom, the top goes within the division sign. If you remember back to division of numbers that you probably learned in elementary school, you start out with the numerator of the fraction within the division sign and the denominator on the outside. So we would start with this out here. So we're doing x squared divided by x squared plus x plus 2. So this looks really weird when you're unfamiliar with the process of polynomial long division. But basically all you want to think about, or all you want to look at, is the leading term. So if we had a bunch of other stuff in the kind of division sign in here, I'm blanking on the word for that. If we had a bunch of other terms within the division sign here, we would still just want to look at this x squared term. Since all we have is the x squared term, that makes it easier to do that. And then same thing out here also, we only want to look at the leading term, basically the term with the highest power x, in this case x squared. So we're basically just looking at this term and this term to basically figure out what we're going to divide by as we go through each time. So when you look at that, you just want to see basically if we do this term in here divided by the leading term out here, what do we get? if we just do x squared divided by x squared, that would just simplify to 1. So basically what we're going to do is we're going to put a 1 right here on top of our division sign. And then same process as doing long division, we would take what we just wrote here and multiply it by all this stuff out here and then write it down beneath here. So 1 times x squared plus x plus 2 is x squared plus x plus 2. Okay, so then what we need to do is we're going to minus all of this. Make sure to always put parentheses around this. We're minusing all of these terms from whatever we have up in our division sign up here. So x squared minus x squared is 0, minus x is minus x, and then minus 2 is minus 2. So once we've subtracted x squared minus all this stuff, we're just left with negative x minus 2. Okay, so then we would again just be looking at our leading term here. In this layer, or this time through, our leading term is negative x. If we were to do negative x divided by x squared, well, that's kind of where we know the problem ends. We can't do negative x divided by x squared and actually get like a number up here. So we're not going to be able to do that. We don't want to write 1 over x up here. That doesn't really work. We just want to think about, basically we want to end up with a polynomial or numbers up here. We don't want to introduce 1 over x or 1 over x squared or something like that. So once you get to the point where the degree of your leading term here is less than the degree of your leading term here, you're done. You just say that our solution of doing x squared divided by x squared plus x plus 2 is just 1, and then we have a remainder of negative x minus 2. So basically, x squared divided by x squared plus x plus 2 is 1 remainder minus x minus 2. So going back to kind of what that actually tells us about this original fraction here, when we do this division, what it's telling us is we can rewrite this division as 1 with a remainder of all this stuff. Well, all this stuff, since it's a remainder, is still being divided by whatever our denominator was. So basically what that tells us is this original fraction we started with, x squared over x squared plus x plus 2, when we divide x squared by this, we get 1 with a remainder of negative x minus 2, which the remainder means that it's still being divided by x squared plus x plus 2. And then we just have the addition there, basically. So that tells us, that long division told us that this fraction here is equivalent to this expression here. Now you might be looking at that and thinking, who cares? What's the point? Like, why is this better than what we started with? Well, remember, what we're trying to do is we're trying to kind of rewrite this out in a form that if we were to be integrating it, if we were to have to go through those steps, we want an easier integral. Well, the reason why this is nice is now we've kind of accounted for one of the situations that arises in a partial fraction decomposition or a partial fraction integration problem. The first thing we did was deal with the fact that the degree of our numerator and denominator were equal. Once we have kind of done that long division to deal with that, now look at what we have. Our fraction, the degree of the numerator is less than the degree of the denominator. So now we can apply one of the other partial fraction expansion methods and break this down, or think about how we could break this down basically in another way. So it pretty much, that long division really just gets us to a point where there's another method that we can actually apply. All the other partial fraction methods don't really work if the degree of the top and the bottom is the same, or if the degree on the top is more than the degree on the bottom. Now that we've gotten it to the point where the degree on the top is less than the degree on the bottom, now we can actually break that up. So really, if we want to just think about the partial fraction expansion form, we now see this fact where, thinking about what's on the denominator here, unfortunately, this expression, x squared plus x plus 2, cannot be factored out. Because if you were to think about factoring it out, there's not going to be any terms that we could multiply to get positive 2 and add to get positive 1. Or in other words, if you think about the quadratic equation, which says that the roots of this denominator would be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What's inside the square root here, b squared minus 4ac, it needs to be 0 or positive. Well, in this case, b squared minus 4ac, right? If we did b, which is 1, squared is 1, minus 4ac, which would be minus 8. What's in the square root here is negative. So that tells us that this expression, this x squared plus x plus 2, has no roots and therefore cannot be factored out. So as a result of that, if the b squared minus 4ac of your denominator is negative, what we know is we're going to keep, if we want to think about the partial fraction expansion, we're going to keep this denominator as it is. It's just going to stay as x squared plus x plus 2. And then basically the numerator, we're just going to write out as like ax plus b. So this is really all we can do for the partial fraction expansion. And then what we would, if we were to actually integrate this, there are methods of integration that we can use to kind of deal with the fact that we weren't able to factor out this denominator. But I'll leave that for another video if you want to kind of continue this problem as far as imagining what that integration would look like. You could kind of pick that up from here. But this would be it for the actual partial fraction expansion of the function. We would get it basically to this point right here, and that would be the solution of this problem. Well, I hope you found that video helpful. If you did, please be sure to hit that like button down below. Hit subscribe while you're down there too, and that bell icon so you're notified of all my new videos. I'll be doing a live stream every Monday night at 5 o'clock Pacific time, like I said, and I hope to see you there. But in the meantime, I have made plenty of other videos about integration. If you want to check those out, click on one of those over there, and see you on Monday.